Well, thank you very much for the presentation. I'm very honored to open this conference. Very glad to be here. So this talk is about conditional VAR, more generally, conditional risk estimation, dynamic models. So the topic of the conference is dependence in econometrics. And in my talk, the dependence will be conditional to the past. So it's serial dependence. So in the financial risk management, a clue notion is to measure risk, and it's traditional to distinguish the so-called advanced approach in which risk measures are based on the conditional distributions from a standard approach in which risk measures are based on the marginal distribution. So the distribution of position or an asset return. And in this talk, I will only consider conditional distribution, which gives information at a given time on the past. So a typical example, which is predominant in the risk measurement, is the conditional VAR, which is defined as the quantile, or the opposite of the quantile, of the returns. So here's a drawing showing conditional distribution here of a return, an asset, and the VAR at a given level alpha is taken as the opposite of the quantile of level alpha. So it gives you information about the tail, the left tail, which corresponds to the loss of the conditional distribution. And there have been other risk measures in any approach proposed in the statistical conditional risk. Another risk measure is, for example, the expected shortfall, which is based on integral of the VAR, which gives other information about the left tail of the distribution. So whatever the choice of the risk measure, the problem from a statistical point of view is to estimate some unknown parameters because the loss distribution or conditional distribution depends on unknown characteristics. And we not only have to estimate such characteristics, but it seems important to have an idea of the accuracy of the estimation. So the accuracy about the estimated conditional risk. And that's called risk measurement, estimation risk, which has to be taken into account when the reserves are chosen, because it can severely modify the the risk which is estimated. And it's problematic to estimate because conditional risk measures are stochastic processes, they are not parameters, and it's not easy to have an accurate, to measure the accuracy of such estimations. So the literature of confidence intervals, for example, for the conditional VAR, it's not very huge. Only a few papers about this topic. So the aim in this talk is to consider the joint estimation of a vector of VARs at different levels. So we have different levels of risk, and we want to estimate them jointly. And this can be generalized to some distortion risk measures, which are other alternatives to the VAR, just like the expected shortfalls. And the idea is to derive the confidence intervals to have an idea of the quality of the estimation for such conditional risk measures. So the outline as follows. I will first present the volatility model and very standard couch line. Then I will describe the conditional VAR and conditional risk measures. Another notion which is interesting to introduce here is the notion of risk parameter, which summarizes the risk. Then I will turn to the statistical part, which is
ฝากไว้นะ
for some
ไม่ฝากไว้
measures
อันนี้มันถ่ายเสร็จแล้ว
asymptotic product which are used to draw confidence intervals. And I will conclude with some small comparative illustration.
แต่ก่อนนี่ใช้วิธีรัน
So
ใน Excel
the
เพื่อคอพีใน
model
Excel ก่อน
installed is a conditional volatility model.
ถ้าพอดัตต้าเบสมาลงทีหลังโปรแกรมเปลี่ยนไปได้
So
ต้องเขียนมาได้
take
เขียน
a long return epsilonty is the difference of two
เขียนเหมือน
price
เหมือนลงทะเบียนต้องชิปอะ
The standard
เลข
modeling is to
ของง่าย
suppose that epsilonty is the product of two variables. One is the volatility, sigma t. So it's a function of the past. So Karlstein model doesn't include additional radicals. It's only a function of the
ๆ
past
คณะภาษา
returns.
SC ปรึกษา
And it's parameterized, so it depends on the known parameter, volatility parameter.
แล้วก็ลบดัตต้าเบส
And
ออก
the function sigma can take several specific forms.
มันไหนเนี่ยแล้ว
For the general presentation, I don't need to
ไอ้หนูจะ
specify
รู้ภาษา
forms.
ภาษาไปหรอ
And we have this process iterative, which is the innovation process, so it's independent
หนู
of
จะ
the
รับ
past.
PHP นู่น
And we only assume that it has a conditional, the square of x has a
มืด
conditional
มันใช่แล้วตายไปแล้ว
equal to
อัน
1.
นี้คนแรกพูดเบรกเลย
So we do not make any assumption on the distribution of theta. It's not necessary to estimate theta because we will use the quasi-maximum likelihood approach. So we only have this moment condition on theta t. The expectation of theta t square equal to. So some examples of volatility models are well known. The standard Gauss introduced by Engel and Boguslev, in which sigma t square is a linear function of the past square returns. This is a very popular way of modeling volatility, and it was successful in many empirical studies, but it doesn't capture an idea which is the asymmetry. We know that volatility tends to respond asymmetrically to past positive and negative shocks. So other models, such as the asymmetric power arch, introduce such positive and negative. And we have other examples. So it's a very general model. Okay. Now, the conditional VAR. So VAR value at risk here is defined as the opposite of the quantile of the conditional distribution. So here we have PT minus 1, which denotes the probability distribution conditional on all the past values of epsilon. And in these models, we have a multiplicative form for the returns, and we also have a multiplicative form for the VAR and for the other risk, most risk measures, in the sense that the conditional VAR at time t is the product of the volatility, sigma, times the quantile, the alpha quantile of the residuals of the innovation. So from a statistical point of view, we have two unknown quantities in this formula. We have the parameter of interest, the volatility parameter, theta, and the quantile of the innovation, because we do not specify a distribution of the innovation, so it has to be estimated. Here is an illustration of the difference between the conditional VAR and the marginal one. So you have here a simulation of returns, log returns, and at a given time, t, which is represented in red in this first graph, we can draw the conditional distribution, which is the Gaussian distribution. For the simulation, we use Gaussian innovations. So the conditional distribution in red is on the second graph, and the marginal one is not the standard distribution, but it can be estimated. And we have here in blue and red the VAR, the value at risk, the same level 1% for the marginal and the conditional distribution. So if we change the point, we different graph, and the conditional quantile for the conditional distribution can be very, the difference between the two quantiles can be huge. In particular, if we are at a very turbulent period with a very high volatility, the difference between the two can be huge. So for setting reserves, it's important to use the conditional formation, the conditional risk measure. Apart from the VAR, it's interesting to introduce other risk measures, and a popular notion in the risk management is the distortion risk, the notion of distortion risk, which is based on an integration over the risk levels. So we introduce a distribution function G on the risk levels, and we integrate out the VAR with respect to these risk levels. So each choice of the distortion function leads to a particular risk measure. And what is interesting here is that for the gauge type model, we still have this multiplicative decomposition of risk. For this DRM, we have the product of the volatility times an interval which only depends on the distribution of the noise. So we have a clear separation between the dynamic of the model, represented by the volatility, and the innovation properties. So a very popular measure in this family is the expected shortfall, which uses uniform distribution of a 0 alpha for the weighting of the bar. And it can also be interpreted as the expectation of the loss, given that the loss is larger than popular notion. But we can also construct some linear combination of bars which enter in these families of distortion risk measures, and we can interpret them as a portfolio of bars based on a vector of bars at different levels and with different weights, pi, taking into account all these different levels. Now we can approximate any distortion risk measure provided that the support is strictly included in 0,1. Using this portfolio of bar, we can easily define two, a lower bound and an upper bound for the distortion. It's useful from a statistical point of view because it will be difficult to derive the asymptotic properties for this distortion risk, but it will be more easily done with the bounds which are. Now I turn to the notion of risk parameter, which summarize the risk in these models. The only requirement on the volatility function is the requirement of positive homogeneity. So we assume that when the volatility is multiplied by some constant k, this amounts to changing the parameter. So it's not a very big requirement. Most volatility functions satisfy this assumption. So we have a new parameter, theta star, which depends on the volatility parameter, theta, and the constant k. So for a standard gauge TQ model, the new parameter, theta star, is obtained by multiplying all the coefficients by k squared, except the gauge coefficient, because the gauge coefficient defines the recursion of the volatility. And so there's only a change on the first q plus 1 for the coefficient. And this assumption of positive homogeneity on the conditional risk is very standard and satisfied by most risk measures. So for a risk measure satisfying this assumption, we have, for example, for the bar, the product of the volatility times the opposite of the quantile of the noise, and for the distortion risk measure, also the volatility times the integral on some characteristics. So instead, we have two representations for the risk under these assumptions. Either in the first formula as the product of the volatility times the risk of the innovation, or the second quality here, it's simply the volatility but with a different parameter, theta star instead of theta. And so we can call this parameter the risk parameter because it summarizes both the dynamics of the model and also the properties of the innovation, the tail properties of the innovation. So for the conditional VAR of Garch 1.1, we have this new parameter, and it's easy to construct examples where the volatility parameter, here I have a numerical illustration of two Garch 1.1 models. In the first model, we have a conditional Gaussian distribution, and in the second model, a conditional student distribution, standardized distribution. And the volatility parameter for the first model is bigger than for the second model, so we have more volatility in the first specification, but we have more risk in the second model. If we define now the risk parameter, we can see that the second parameter is larger for the second model. So we can say that the first model is more volatile, but less risky than the second for this notion of risk. So let me now consider the estimation of these risk measures. So the model is summarized here, and I will focus here on the VAR for the moment. So the VAR, the conditional VAR, is the product of the volatility times the quantiles of the innovation, and the natural method to estimate it is a two-step method. In the first step, we estimate theta by quasi-maximum likelihood, which doesn't require assumptions on the noise. And in the second step, we estimate the quantile of the residual. Using the residuals, we estimate the quantile of the innovations. So it's correctly method, but the asymptotic properties are not very much known. So that's what we derive now. So in more details, in the first step, we need to define the volatility, to define the quasi-maximum likelihood. So it's necessary to introduce some initial values to the volatility specification. Asymptotically, we show that these initial values don't matter. And in the second step, we derive the residuals on the first step estimation, iterative method, and we can compute the empirical quantiles for these residuals. And these will provide an estimator of the VAR. I will be very brief on the assumptions. We have strict stationarity of the stochastic process of epsilon t, a small noise, a small moment assumption, and other assumptions, smooth assumptions, which are required to show that the initial values don't matter asymptotically. So we also need an assumption to estimate the quantiles of the innovations. So we have an assumption that it has a density which is continuous and strictly positive only in the neighborhood of the quantiles of interest. So of course there have been some results in the literature concerning the asymptotic properties of sample quantiles. So they were derived IITK and Weber. And also there are some extensions for stationary processes. But in our case, we do not have a stationary process because we are working on residual. So it's not a stationary process, it depends on the size, it depends on M and on the estimated parameter. So it cannot be stationary, and we cannot use such results. So here is the joint asymptotic distribution for the parameter, theta, the volatility parameter, and the quantize of the innovation. So we retrieve for the parameter theta the information matrix, the QML, and interestingly, for the quantize, we have an asymptotic variance, theta, alpha, which depends on the levels of risk, summarized by alpha, but do not depend on the parameter theta 0. So the accuracy on the quantize, the estimated quantize of the innovations do not depend on the parameter theta 0. However, there is an effect of estimation. The last equality here, the last term would correspond to the estimation of IID quantize of the IID process, and the first three terms are the effects of estimation. And the effect of estimation on the estimation of the first step estimation on the distribution of the quantize can be positive or negative. It can increase or decrease the asymptotic variance. We skip this. And so we can estimate, using this two-step approach, conditional bar simply by this formula. And the interest is to derive the confidence intervals for the conditional bar. So we are using the asymptotic distribution. So at the given level alpha 0, so it's important to distinguish this level alpha 0 from the other risk levels alpha I. So the first risk level to correspond to the risk, market risk, while this alpha 0 corresponds to a statistical risk, estimation risk. It's not, both are. So we can also derive confidence intervals for vector portfolio of bars, or linear combination of bar, and it's very similar. And finally, we can choose the ways to approximate distortion risk measure. So, distortion risk measure, which is defined with a distortion function G, can be easily estimated. It's given by this equality. So we retrieve the product of the volatility at the estimated parameter theta hat, times this sum, which corresponds to weighting defined by the function G of the empirical quantize of the residuals. So it's easy to define the estimator, but it would be very complicated to derive the asymptotic distribution of this estimator. So an alternative is to use the lower and upper bound, which are obtained by the bound. So we can use the lower bound for using a linear combination of bars and the upper bound, which were defined before. And thus we can derive a confidence interval at significance level bounded by alpha 0 for this distortion risk. So I turn to illustration on 9 stocking cases. So the sample period is from 1991 to 2011. And for simplicity, we use, and also because it's the most widely used models, we take Garch-Rowan models for this series of log returns. So we have 3 parameters in theta 0, 3 coefficients, intercept omega, the arch coefficients, A and the Garch coefficient. We not only estimate the bar at a given level, but we want to consider the distortion risk measure. So we take the integral of the bar over some interval alpha 1 and with 2. We are interested in extreme risk here, so alpha 1 is 1%, which corresponds to very extreme risk, and alpha m is 10%. And we use this distortion function, for example. So we estimate the distortion parameter, risk parameter, theta star, which incorporates both the volatility parameter and the distortion function. So, as previously, the theorem parameter is estimated by this quantity, and we can obtain confidence intervals using the approximations like lower and upper bound for the term. So these are the confidence intervals obtained for the 9 assets. So for the risk parameter, the 3 components of the risk parameter, we have in blue the estimates, and we have the confidence intervals where we can compare the accuracy of the different estimates. And the estimates of the Garch coefficients B are very close, very similar among the 9 series, but there are some important differences in the Arch coefficients A and also in the intercept. And in general, the more volatile, the less accuracy of the estimate. And finally, I will be showing a graph of the confidence intervals for the VAR estimation. So here we have a series of logarithm for the DAX index, so one of the index. And in green, you have the opposite of the VAR, because we have interest loss. It's more interesting to draw the opposite. And the opposite of the VAR at 10% and 1%. And in the middle, in red, we have the distortion risk measure, which is an average, sort of average for different levels of risk. And we, using our results, we not only have an estimate of these risk measures, but also confidence intervals. So they are drawn around the curve, which gives you the accuracy of the estimation. So I think, to conclude, thank you for your attention. You have some questions?
No. Question, any question or comments?
Yeah. Yes.
So in your method, you separately estimate the quanta and the Garch parameters, right?
Yes.
But it could be so simple to some kind of lines. So maybe you can use the quanta level, regression quanta maybe combining them together, not separately.
Yes. Yes. We have in a related paper, we use a regression time to estimate jointly the risk parameter.
Also, so is there any theory to select G?
So G is chosen by the statistician. It depends on your aversion to risk. If you're more averse to risk, you weight more the extreme risk.
So you just predetermine G?
Yes, G is given. Yes.
Okay, thank you.
Thank you very much, Professor. Your paper is so interesting and it is so enjoyable. But I have two quick questions. The first question is that because your paper is a multi-level conditional bar estimation in dynamic models. But I wonder that if we use the approach of the extreme value conditional bar, could it be possible to do so? And the second one is that because of the advantage of using the extreme value is that we don't have to specify any function form of the marginal. That's typically the case. And the second one is that if so, what is going to be the expected result are going to be different or similar to your approach? Thank you, sir.
Sorry, I didn't catch the second question.
Second one is that if it is possible to estimate by using the extreme value theory and then conditional multi-level, then my question is that if so, what is the expected result from the estimating two approaches? Are they going to be different or are they going to be similar? If so, why? And what are we going to choose between these two approaches?
Yes, indeed, there are some papers using extreme values for these conditional models. We didn't consider this approach, but it works well with very small values of alpha, very extreme risk. Here we are interested in moderate risk, so the values of the levels of risk are not so close to zero. So we cannot rely on very extreme values in this case.
Related to some questions, what you are doing is you're doing risk and estimate that at different level. In practice, I think that the measure can be so distortion what I mentioned is now any comment on how you do that for equivalent distortion risk management?
This is a new topic I don't know how
because what I have in mind is precisely copula. In order to very distortion risk management, what I mentioned is very easy. What I mentioned, you take a distribution, you take a function from 0, 1 to 0, 1, you compose with that, you distort the distribution function and another one. So let's say dimension 2. So the distortion should be something function on the unit square. And that is very similar to a copula. So distortion of the copula might be a new topic for research and information.
Thank you. And I want to say same question whatever is asked for this G. Can you put it back to your slides for the last part? Selection of G. Last part of the topic. Your simulation results.
G.
Yeah, the selection of G. Back the last part. Last part of your talk. Your numerical result, yeah. Oh yeah, this G. Why you choose this kind of G? This is very simple. Do you have any other choices?
Yes, you can. It's just for illustration to choose this one. But it's exponential type of G function which is used financial risk management. You could choose another one.
So you use this G for your simulation result. So your blue line and all the other lines they are quite apart.
Yes, it's for the sake of illustration, but I think you change the much change.
แค่พูดบอกว่าทำไมงานที่เราต้องได้ใช้เยอะนี่ก็สำคัญ
Distribution function G, you can find it.
Yes.
ได้แล้ว
Any other questions?
ใช้กูติดมันก็มีหูซ้ำๆเดิมๆเนี่ยเลยแบบว่า
I'm interested on your empirical result. Could you go back to the plot with VAR estimate with the red line? Oh, yeah, that one. Is this out of sample forecast or just in sample?
It's out of sample.
So how many days?
เขาบอกออดิโอกับซาวด์ต่างๆออดิโอคือเสียงซาวด์กับแปลว่าเสียง
100 or
ลอง
200
เกิดแปลว่าเสียง
days
ทุก
here.
วันนี้สับ
But
สน
you use only 1 day VAR and do the moving window?
So we estimate the volatility parameter on the 3,000 observations.
So how do you judge
Nếu
the
mà có sound
performance
lighting thì nó
of
có
the
thể
proposed method? Do you calculate vibration rate?
So we can compute the number of violations of the law, and it corresponds approximately to the normal rates.
So what is the performance for the vibration rate?
Sorry,
มันคือว่าตอนที่เปิดไอ้ตัวไฟมันก็แยก
we
เอา
did
เลย
not introduce a observation components.
Just
Just illustration of the
ห้องโอเคเลยที่ไอ้ปิดเปิด
length
ต้อง
of
มีปัญหามั้งเดี๋ยวเราออกไปเราได้ออกไปน้องแวะไปพอต้องเรื่อง20ก็201กับเรื่อง202แวะพอไปแล้วว่าให้เปิดตัวไว้ก็ได้ให้เปิดถึงเช้าได้
No, we didn't do
ถ้า
it.
แบบไปคุยอยู่ไหน
it's requirement
ถ้าไปแวะสเตลนี่อาจจะลงแวะเปิดพอส่วนนึง
Any other questions? Otherwise, let me